I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for these students. I just ask that you bless this class, help me to remember all the things I was going to talk about today and to talk about them sensibly. Help us to glorify you in whatever we do here, Lord. In your name I pray, Lord Jesus. Amen. So here we are. This is lecture 21, Math 115. I've got a little bit more to tell you about geometry and topology, so let's get right into it. So I brought some toys today. I wanted to talk a little bit more about, let me just sort of put some topics that I'd like to talk about today. I'd like to talk a little bit more about geodesics. I'd like to talk a little bit more about ideas of distance. All right, and I'd also like to show you an example of conformally related geometry. Let's see here, what else do I need to show you about? There is one other thing that we're talking about today. Geometry, topology 2, and mathematical systems. So mathematical systems is, that's going to be a kind of a shorter discussion. All right, so let's start with the geodesic. What is a geodesic? So a geodesic is, just a reminder, there are, just to recap last time, what did we learn? What was the big thing we learned? So there are, in terms of geometries, we learned that there was Euclidean geometry, there was hyperbolic geometry, and there was spherical or elliptical geometry, right? And each one of these is special, different from the other, right? So Euclid, and they're all characterized by how they deal with either modifying or leaving intact Euclid's fifth postulate, right? Euclid's fifth postulate says that given a line, for a given line, right, and a point not on that line, there exists a unique line going through the point. That's Euclid's fifth postulate, right? If you modify the fifth postulate so that for a given line and a point off the line, there exists more than one line going through the point, right? More than one parallel line going through the point, I should be careful. Then we get what's called hyperbolic geometry, which was discovered by Lobachevsky, Bolyai, also Gauss, arguably. At least those three people, probably more, honestly. And then there's the spherical geometry, which was discovered a little bit later, or at least thought of in this way a little bit later. This was Riemann. So I'd like to talk a little bit more about Riemann today, also. So hyperbolic was Gauss, and I won't try to spell it. Loeb and Bohl. I'll just abbreviate that. Euclidean. Well, who wrote the book on Euclidean geometry? Euclid, right? So Euclidean geometry is very old. Of course, hyperbolic and spherical geometry much more recent. And so both of the hyperbolic and the spherical geometries, these are both collectively referred to as what? These are both collectively referred to as non-Euclidean geometry. All right, so I'd like to talk to you today a little bit more about that. All right, but first I think I should just go back and let's just talk about geodesics a little bit more, all right? So I brought some props today to help with that. The one is this, all right, so it's a somewhat, I don't know what this stuff is on this ball. Well, hopefully it's I don't know. Anyway, whatever it is. I found this on the floor at my house. So my child probably is missing it now, but they won't watch this video, so my secret's safe here. Don't tell my children. None of you know my children, right? No, so it's fine. But this is, roughly speaking, a what?
Sphere.
Sphere, right? So if you want to make it like the Earth, do this, right? Right? The Earth is an oblate spheroid, we think. So what are the geodesics on a sphere? Well, there's one, and so unfortunately the line here, pretend that line is straight, right? So if you follow this line all the way around, all the way around, that's what's called a great circle, right? A great circle is one that goes all the way around like that, right? Now, if you were to follow, let me show you something that's not a great circle. So if I do like this, that would not be a great circle, right? Great circles have to go all the way around, right? So even if I did this, right? Even if I went like this, see that? So this one went all the way around like that. That is not a great circle, all right? So before long, my hands are going to be covered with marker ink if I'm not careful. But so if we look at the great circle that is in the middle of the ball, right? There's no other great circle which is parallel to that. All the other great circles, like if I draw another one, I'll try to draw it in a different color here. Let me see how, let me try out red. So if I draw a great circle like this, I'm trying. Oops. I think this was ill-advised. I bet I won't get back right. Oh, I did, kind of. So there, roughly speaking, is another great circle, right? And so if you look at this point off the this one right here, any kind of great circle you put through that point, it's not going to be parallel to the original great circle. So in other words, the fifth postulate for a spherical geometry, and this is an example of a spherical geometry, the fifth postulate is modified to say that there just isn't even a parallel line through that point off the line, all right? So that's a spherical example of geodesics on sphere. I can show you some more geodesics, so let's look some more examples of geodesic. So let's talk about, come on, geodesic on a cylinder or cone. All right, so watch this. If I take this point here, right, and this point here, let's say P and Q, right, and I connect those points, yeah? Just a second, I brought myself a ruler in here somewhere. Oh man. So if I connect those points, right, like so, I'll use a red line here. I just wanted to show you guys what geodesics look like on a cylinder or a cone. I mean, there are more than one, right? But one way you can sort of illustrate the geodesics on a cylinder or a cone is just to make one. All right. So here, if I just take this paper, right, and I just curl it up like so. All right. Now, I'm trying to get this to be like a right circular cylinder, right? If I did it right. Sorry. I'll eventually get it right. So if I think that's roughly right. All right, so like that. So if you can see that line, that curved line, if you study the distance function on the cylinder, the line of shortest distance between point P and point Q on the cylinder is exactly that line that we're looking at. So that's the kind of neat thing, to see geodesics on spaces which are formed like if you can form your space by just rolling up a sheet of paper, then the straight lines on the paper become the geodesics on the surface. It's just that. And so a cylinder can be formed by just rolling a sheet flat like that, right? And also a cone can be formed like that. So if I took a cone, for example, here's a cone, right? I'm trying, guys. I should have brought some tape. Oh well. So here's a cone, right? And the shortest distance between 2 points on the cone is also given by that, like that. Now, I should be careful. What's the issue with the shortest distance between 2 points on a cylinder or a cone? What could happen? You might get into trouble, right, if you did something like this. If I roll this up nice and tight. Oh, phooey. Just a second here. Let me give myself a bigger one to work with here. I need names for 2 more points. How about R and S? There you go. What, do you think I was going to say something stupid? Don't worry, there's still time. So if we look at that one, right, if I did this, all right, I'm trying to make this, so here we go. Now that's kind of a fatter cylinder, right? So that purple line between R and S, right? Follow it around. You can see it, right? If you can imagine that. See that line all the way around? Is that the line of shortest distance between R and S? Well, it's not, right? Because you could connect around the other side, couldn't you? See that? Like if I had a third hand, we could draw the marker between R and S directly, right? Let's see if I can do it. Like this, right? This would be this would be the shortest path, wouldn't it? So that is one of the troubles with geodesics. If you have a space which curves back on itself, this can be a problem, right? Does that make sense? Why the red line would actually be the geodesic, the shortest path between R and S on that cylinder? I hope this makes sense. Okay, so that's just a little bit more on what a geodesic is. So geodesics are the paths of shortest distance on on some space where you have some notion of distance, right? So let's talk a little bit more about that. All right. So in your homework, you have some hypothetical problems about a kind of weird notion of distance. So let me show you something kind of perverse here before we get to your homework example, if you don't mind. Check this out. I want to show you something slightly disturbing, perhaps. So suppose we have a triangle, let's say a 3-4 triangle. So here I go 3 units over, and I go 4 inches up. Oh, poor planning on my part. Let's try that again. I go, let's say 4 units over, right? And I go 3 units up. What's the length of the hypotenuse on this right triangle? Can you tell me? So this is, this is 4, this is 3, right? How long is the hypotenuse? What's that? 5, yeah. So you can even measure it, right? Here we go, 1, 2, 3, 4, 5. Yeah. So I'll put it in red. So here we go. 5. So I want to show you something weird that maybe will bother you, maybe it won't. I don't know. What happens if we take this journey going 4 over and 3 up and we divide it into 2 steps, yeah? So page was I on 3? Yeah. So check this out. So if I go 2 over, right? And then I go up 3/2, right? And then I go 2 more over and then up 3/2. I could go this purple path, right? How long is, this brown path. How long is the brown path? You got 2, you got 2, you got 3 over 2, you got 3 over 2, right? So it's still what? What's the length of the brown path? Well, it's not equal to 5, is it? It's 2 plus 2 is 4. And it's what? The brown path has length 7, right? Do you agree? Because we go a net of 4 over and we go a net of 3 up, right? But you could take that and you could do a green one, right? So the paths I'm adding here, they're always horizontal and perpendicular stair steps. So I go 1 over, I go 3/4 up, I go 1 over, I go another 3/4 up, I go 1 over, I go 3/4 up, I go 1 over, I go 3/4 up. See that? So the green one, still length 7, right? But what can you do? You can keep doing this, right? So I'm going to run out of colors. Let me just do the rest. Well, I'll do one more. Here's black, like this, right? I can go like that, 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 like this, like this, like this, like this, like this, like this, like this. Still length 7, right? And I can do this again, right? I'll use pink. I never use pink. Like this, like this, like this, like this, like this. We could be here all day long, right? You're like, no, we can't. I'm going to break. You can't stop me. Let's see here. It's true, I can't. So still length 7, right? And I can subdivide it further, right? Like mathematical plinko. So here, you see what I'm doing? So then, that's about the last one I can draw. It's still length 7. So doesn't it stand to reason then that the length of the hypotenuse should be 7? Because if you take the limit as these stair steps get really, really tiny, don't they exactly match up with the hypotenuse? So shouldn't the length be 7, not 5? What do you think about that? You're like, but the length is 5. You're right, the length is 5. So what's wrong with that argument then, this idea? It gets infinitely close, right? If you take the stair step up to the hypotenuse, it gets as close as you want it to get, right? So this is the trouble with mathematics, is sometimes these kind of intuitive fuzzy arguments, they fail. Because there's actually something really, really technical about taking that limit that I'm talking about. And the technical thing is that the stair step path, it is not what we call smooth. It's not a smooth curve in the sense of Euclidean geometry. And so it actually doesn't make sense to take that limiting process and compare the Euclidean distance with this other weird distance. And this other weird distance that has this path, the stair step path, it does have length 7. That's actually an example of what your book calls city geometry. So city geometry, let me describe more completely. City geometry means that the only way you can travel from point A to point B is through a series of like east-west or north-south paths, right? So in terms of the city geometry, it is true actually the distance between say point P here and point Q here is in fact 7 in terms of city geometry. So let me just write that explicitly. So here's the notation. The distance in the city from P to Q is in fact equal to 7. But the distance Euclidean from P to Q is, as we said from the outset, 5. And these are inequivalent notions of distance, and you can't just freely go from one to the other in terms of some limiting process, because it doesn't make sense. Now, we don't write out city in Euclidean every time, because that gets really, really old. So what we're going to write is dc for city and de for Euclidean, okay? And I owe you some better formulas, because this is just an example, right? So the formulas for the city geometry are as follows. There's a homework problem on this, so I'm trying to be somewhat specific here. So the d city, if I go from, say, x1, y1 over to point x2, y2, all right, then that's equal to the absolute value of x2 minus x1 plus the absolute value of y2 minus y1. In contrast, the Euclidean distance from between these points is given by a somewhat uglier looking formula. It's the square root of the sums of the squares. Right, like that. So let me, if I can find it. Come on. Well. Sorry guys, I don't know where I set your homework, unfortunately. All right, well, the homework has stuff about city. Oh, is this it? Ah, that's college algebra. That's no help to us. All right, anyway, I brought everything in the kitchen sink today except for your homework, so it's okay. We'll make do. Example 1. So the idea is that on a city you have, you know, I know this only partially makes sense in Lynchburg, right? But there does exist part of the city with roads that are laid out like this, right? I mean, I know it seems kind of laughable if you've actually driven through Lynchburg, but pretend with me, yeah? So in a city, the roads are laid out like a grid. Now, like this, okay? So here's a city, and we can ask the question, what's the distance between, you know, and we can say that the origin's here, right? There's City Hall or whatever, right? So maybe this point would be -1 block, -1, -2 would be this point. And then over here would be, let's see here, that would be 2 over 1 up, so that would be 2, 1. And then the question is, what's the distance that you actually have to drive to get from point P to point Q? That was supposed to be a Q. Now here, and this is also where the whole example gets a little bit kind of silly, is it assumes that the city has roads that go both ways, but we've all experienced this in cities that have these kind of grid roads. They're always one-way roads, aren't they? So this whole discussion really breaks down in that regard. But anyway, ignoring that for a second, so to get from point P to point Q, what do? You got to drive, I mean, you can drive like this, right? That's one possible path, right? So that would, the distance of this green line, that would be what we would call DE, right? So DE, excuse me, DC, the city distance from P to Q is what? So we do the absolute value of 2 minus 1 plus the absolute value of 1 minus a minus 2, which is a fancy way of saying 3 plus 3, which is equal to 6. So you have to drive 6 city blocks to get from point P to point Q. Does that make sense? But the thing is, of course, you could have driven other ways, right? It doesn't matter. This is the kind of funny thing. If you drove like this, right? I don't know if you thought about this, but if you drove like this, ignoring the time for stoplights and junk like that, that's not part of this analysis, then this orange path would also have length 6, wouldn't it? See, because you're just going 6 blocks. You go 1 block this way, 1 block, 2 blocks, 3 blocks, 4 blocks, 5 blocks, 6 blocks. So still 6 blocks, right? This is sometimes called taxi cab geometry. Now, in contrast, what is the Euclidean distance from P to Q? You could also call that, sometimes we say it's the distance as the crow flies, right? Have you ever heard that? Have you ever heard that saying? No? No? Or the line of sight distance? So like from here to there, the length of that line, the Euclidean distance would be what? It's the square root. So these same numbers appear, right? Do you notice the formula is the same? That's 3. This is 3. See this? This right here matches that right here. This right here matches that right there. It's the same numbers you're using, just in a different way. So we do 3 squared plus 3 squared, which is the square root of 9 plus 9, which is the square root of 18. I think in the homework problem it asks you to approximate your answers to like a tenth or something. And the unit of distance it's using is city blocks, which okay, fine. That's a reasonable unit of distance if actually all city blocks were the same length, which is probably not the case. Don't think too hard about this. Anyway, so that would be 4.2, if you like. So, and that's in terms city blocks, right? 4.2 blocks, whereas this is 6 blocks. Now, how could you shorten the distance from P to Q, right? Well, if you had a drone, you could just fly the straight distance, right? Or if you had a helicopter, whatever. Any questions? Does this make sense, what I'm talking about? Yes, no, maybe so? All right, so that's taxi cab geometry. Now, I want to talk to you guys a little bit more about so this is a modified notion of distance, right? So like, fun fact, other distances. Other distance formulas. So while I'm on the subject here, you can define the distance from like a point x1, y1 to a point x2, y2 as equal to the pth root, watch this here, the pth root of the absolute value of x2 minus x1 to the power p plus the absolute value of y2 minus y1 to the power p. So this is the pth distance function. So like, here we go. P equals to 1 gives us, well, P equals to 2 rather, gives me the Euclidean case, Euclidean distance. P equals to 1 is the city distance. All right? And there's others, but the interesting thing is you can define a circle in this context. What's a circle? Circle, set of points equal distance from center, right? And if you do that, and like we could go back to my grid here for a second. What's a circle in the city geometry? It's a little bit funny because you have to have well, The harder thing to think about is to understand it completely. You have to let the grid become very, very dense and like be able to think about the grid reaching all points. So it's a little bit fussy there. So let me not get into all that. Your book kind of does that in an example, but here's what it looks like. So you know what a circle looks like in Euclidean geometry, right? The circle in Euclidean geometry, well, we know that one, right? That just looks like this, right? Circle, right? And it turns out that in the taxicab geometry, if we're talking about the same deal, the circle relative to the same center point with respect to the city geometry, it's a diamond. Turns out to be a diamond. So these are the points which are distance, let's talk about unit circles. These are all the points distance 1 from the origin in the city. So in the city geometry, the circle is actually what we would in standard language call a diamond, right? And here's the thing. When you look at like p equals to 3, well, you know what? Rather than doing this, I should really show it to you in a proper thing. Let's see here. Okay, so I need to use the computer to show this more properly, but I'm trying to avoid using the computer until I'm done with everything I'm doing by hand, because as we know, when I turn this off, there's no guarantee it's coming back. So you'll forgive me for my lack of continuity here. I'll have to circle back to this. My point to you is that these are both circles, just with respect to different geometries. So you can actually take p to be infinity, and like if you take p to be infinity, that gives you what's called the sup norm, or as I like to call it, the sup norm. Sorry, that was a horrible joke. Which would make more sense if I'd written out sup, but which is sup. So this is actually the circle with respect to the infinity distance. I said norm. I don't know what that means. So here, this is the let's say d infinity circle. So sometimes philosophers talk about the impossibility of squaring a circle. And I always like to mention to philosophers that that's really not a good turn of phrase, because mathematicians have been looking at square circles for like 100 years, maybe 150 by now. Like, these are all circles with respect to different ideas of distance. So, anyway. Okay, so a couple more props to get out here today before I get back to the computer. All right, so I mentioned the idea of conformal. What does it mean? What's conformal? Let me talk about conformal for a second here. Conformal means basically preserves angles. Preserves angles. You can also talk about something being, you can talk about an isometry. This means preserves angles and distance. Isometry is the idea behind congruent triangles. Like, for example, or hexagons. Here you go. Check this out. So this hexagon right here is isometric to this hexagon over here. See, I can map hexagon 1 to hexagon 2 by this function, right? And if I do that, all of the lengths of the sides and all the angles of the hexagon, they're all faithfully preserved, right? That's an example of an isometry. A conformal mapping is something a little bit weirder. Actually, it's something a lot weirder, but let me show you. So 6. So I brought a prop here. And I think I'll probably have to turn off all the lights in here to make this one work. And I probably should shut those doors. Still going to be fighting off the light pollution from the screen up there. All right. Let's see. I'll try it back here. See if you guys can see this. So look up at the ceiling, if you will. Do you guys see that? Let's see if I can get it over here. It's too faint over there. If you look up at the ceiling, do you guys see the cross there? Yeah, let me see if I can. I'm not sure. I'll try over here. This is all a little bit dicey, but see, just a second here. Can you guys see that?
Yeah, we can see it.
Yeah.
So what do you see? Do you see right angles, right?
Yeah.
If I did it right, you see a grid of right angles. But what is this? It's a sphere. How do you get a sphere to have right angles? See, this is a sphere, but what's been laid on it is this grid, right? And it's not a uniform grid. It's kind of cleverly laid out. And what this grid is a conformal mapping. It's a conformal mapping of the plane onto a sphere. Actually, this ties in with that Poincare thing I did last time. They're part of a larger story, but here's a picture of the toy I was just playing with, so you can see it here better. So what happens is if I put the light here, right here at the where the pole should be, then the light rays go out in such a way that when they travel to the plane, which was the wall, that's the mapping. Basically, the correspondence between the sphere and the wall is that light traveling through the sphere. Anyway, that's an example of a conformal mapping. See on the sphere there's right angles, and that maps to what you can obviously see as right angles on the wall. Okay, so do you guys ever wonder how big this room is? 548 inches. How many feet is that? $607 inches. What's that? That's what, 50 feet? I think that's 50 feet. This room is 50 by 50. Who knew? So if the room is 50 by 50, fun question. How far is it from one corner to the other in the city distance? 50 plus 50, it's 100, right? How far is it in terms of line of sight? You got to do what? The square root of 50 squared plus 50 squared, right? What's that? I don't know right offhand. Here we can do it. 50 squared plus 50 squared. Square root that thing. So the answer is about 70.7 feet line of sight from one corner to the other. Now, annoyingly, there's doors in the corners, and there's this funky thing in the corner, right? But I can kind of get it. No, let's see here. Aw, man, error. Stop that. I'll just try it from here. error again. I can't hold the thing straight. 780 inches. We got to divide by 12 to find out the number of feet. What's 780 divided by 12? 65, because the stupid door's in the way. And you could see how it would be about 5 more feet if I could actually get to the corner up there. Oh well, I tried. Do you guys have one of these? It's a laser measure. You know what these? They're like 20 bucks now. They also make ones that go both ways. So you can hold it in like the middle of a room, and it'll shoot a laser one side, a laser to the other side, and tell you what the, width of the room is. Things like that. Okay, so anyway, a few more things to show you in my show and tell lecture. Check this out. What's that? It's messed up, right? So we're turning the sphere inside out. This is actually based on a mathematician's work back in the 70s, I believe. Let me show you a little bit about that. Well, if I can. These videos are too long for us to watch in their entirety, so I'll just try to skip ahead around in them for a minute, but I just want to give you a sense of it.
Mathematicians can turn a sphere inside out.
Yes, that's true.
What's the big deal? Poke a hole in it, pull it through.
Sure, but the point is to do it without making a hole.
But then it seems impossible.
You're right. You cannot do it with an ordinary sphere, like a basketball. You have to understand the rules of the game. This sphere is made of an abstract elastic material that can stretch and bend and pass through itself. But you cannot rip or puncture this material without destroying it, and you cannot crease it or bend it sharply.
If the surface can pass through itself, what's the problem?
Do you think allowing self-intersections makes it easy? Try it.
I'll push the two halves right through each other.
Be careful. What about that
Ooh.
lip around the equator? Remember, you mustn't tear or crease it.
Let me try again.
That's no good either. You're pinching it infinitely tight.
But then there's no way. It's impossible. You have to crease or pinch it to turn it inside out.
It is surprising, but watch this.
Is this it? Is this a sphere turning inside out?
You bet. That
That's-
wasn't easy to follow, was it?
That's the toy.
To figure out what's going on, let's look at something simpler. A circle.
So anyway, I will give you guys links.
One circle, so that we can color the two sides differently.
I will give you guys links if you want to watch this. It's about 20 minutes long. There's 2 parts of it. It's made by the University, I think, of Minnesota about, 30 years ago. So still, the graphics still hold up, I think. Let's see here. So this is the day we're having fun. So I guess I probably should get you guys eating, because I don't think you really need to write anything we're doing for the rest of class. Listen, guys, I have donuts. Should I pass them around? I'll pass them around. If you want a donut, take one. I also have homemade chocolate balls. Not chocolate balls, peanut butter balls. So if you have a peanut allergy, you're allowed to take 2 donuts. But my wife kindly, so I'll pass it from the back to the front and from the front to the back. So once So you guys pass over there and then up to the other side. You guys start here and pass up, yeah?
Thank you.
Thank you.
So my wife, I told my wife I need to bring you guys something today. And I know there's like course evaluations coming up soon, but this has nothing to do with those. I don't just bring snacks when we have course evaluations as some sort of bribe. That's not what this is. Check it out. Oh man. Oh. I'm sorry. I seem to have, well, you'll have to be careful when you pick these up here. My wife made these nice little paper cups, and then I put the thing sideways, and they've kind of come out of. So if you could take a cup and a chocolate if you want, and pass them back if you're interested. These are peanut butter balls. So if you're allergic, you know. All right. So, so yes. So one of the things I always try to talk about. So one of the things I always try to talk about around the time of course evaluations is there's a question on the course evaluation that says, was the biblical worldview, it's something along the lines of, was the biblical worldview, did this course integrate biblical principles or something like that? This is one of the questions. And I think mathematicians suffer from this question because so many students labor under the misconception that math isn't biblical, that there's no biblical worldview in math. And I think students are often confused by the question because they're like, you know, I factor this polynomial, then, you know, oh, well, after I read Psalm 23 this morning, all of a sudden I saw how to do it, right? I mean, it's not like that, right? But I always try to tell students something along the lines of this, is, well, who's the author of truth? Right? God is the author of truth. And is math truth? I think we can all agree that math is truth, certainly. And so if you say that math doesn't have a biblical worldview, if math is not biblically integrated, then I guess you're saying that math is not part of God's truth. And that seems like a bad thing to say. So when you read that, you know, course evaluation question, you should just say, yes, of course, there was biblical integration. Easy. And by the way, whenever you see not applicable, like hitting not applicable in the course survey is worse than like strongly disagree, because they just grade it on like they just take one number from all the selections, right? So if you get not applicable, it's actually very bad. It's not like saying you're neutral. It's not like it's just avoided, you know? Anyway. But again, these snacks have nothing to do with the course evaluation. It's purely coincidental that I'm talking about it right now. Any of you guys ever want to write a math paper? No. Wrong answer.
It's like an extra credit thing.
No, this is, we'll do it all together. So who wants their name on the paper? Anybody? Anybody? Anybody wants their name on the paper?
Sure.
Sure. What's your name?
Taylor Guerin.
Taylor Guerin. How do you spell your last name?
Garran.
A-N. Anybody else? Author two? What would you like your name to be?
Caden Friedman.
With a C?
K-A-I-D-E-N.
K-A-I-D-E-N?
Yeah, with a K.
Oh, with a K. And then Friedman, you say? F-R-E-E-D-M-A-N? All right. And we'll add some famous names. All right, well, four authors. Here we go. Are you ready? Let's see what we got. This is MathGen. So, quasi-discretely compact curves of composite ideals and uniqueness, Taylor Guerin, Caden Friedman. M. Wiles, and Z. Deligne. Recent interest in factors has centered on computing additive points. We show that Smale's conjecture is false in the context of homeomorphisms. Next, Wantami improved the results of D. Darboux, deriving co-surjective empty factors. Hence, unfortunately, we cannot assume that equation. And it goes on. Listen, it doesn't just take the same paper and put names on it. It generates genuinely different nonsense papers every time. And so to prove a point, they did this, and they have submitted these to certain electronic journals online and got them published. So, yeah, it's a problem. But I like these people. They have made a silly paper generating thing.